Matthew Rocklin, awesome guy who contributes to SymPy, just got snagged by Continuum, and he's going to talk to you today about functional performance with core data structures. Give me a hand.
Hi, everyone. Thanks for coming. As she said, my name is Matthew Rocklin, and we're talking about functional performance with core data structures. You have a question? You can't hear. Someone can't hear. Can the volume be changed? Is everyone else OK? Oh, a little louder now. Great. Thank you. OK. Disclaimer, this talk has benchmarks in it, and benchmarks you shouldn't trust. It's also sort of a new thing, so people haven't ripped into this yet. So it's experimental. Don't judge too harshly. OK, so the sort of synopsis is I'm going to claim that pure Python is not always slow. It's slow in many cases, but not always slow, and we don't want to sort of make that always claim. And then Python is a decent functional language. So we're talking a little bit of functional programming, not too much. So it won't be scary functional programming, I promise. OK, so we have this intuition that Python is a slow language. And so here's matrix multiply written in Python, pure Python, no fanciness around it. And it is slow. You should not be doing matrix multiplies in Python. It's a sort of 10 or 100x slowdown when we use Python over some C system. But of course, there are very nice C systems that we can use to hook into Python. So that's sort of one. We usually think of Python as being slow, so we hook into C. And that's one story for numerics. But that benchmark was a numeric benchmark. And I claim that we often take that intuition and we apply it to other cases where it doesn't apply. So what about all the other cases? What about if we're not doing numerics? Is Python still slow? That's sort of the question I want to ask. OK, again, this talk has benchmarks in it, micro benchmarks. Micro benchmarks are hard to do well. You can rip into them pretty easily. They're intended to sort of just give an idea. So don't trust everything to sort of take ideas away. And for best performance, you should understand your problem. That's always the best thing. OK, so one thing Python performance has going for it is this idea that its core data structures are actually very, very fast. The Python dict is often cited in scholarly articles as an awesome dict. So you'll actually find it in native C code. You'll find C code that imports the Python dict and uses it, despite not being in Python at all. So Python has these really great core data structures going for it. So here's my common little benchmark to show off the speed of Python data structures. Here's a frequencies function. We have some collection. We want to count how many times each element in that collection occurred. So here we have some list of names. We make it sort of long artificially. We call frequencies on it. We get a lot of counts. We often do computations like this. It's sort of the basic computation that's hard to do numerically unless you know your data ahead of time. And so we can ask, how long does that take? We had how many elements do we have? We had about 7 million. We can count them in about a second. That's just naive Python code. That's not C-based or anything. When I bring up frequencies, people always tell me about the counter object and collections in the standard library. That's actually a lot slower than just naive Python. But they're doing other things. That's a more complex data structure. Today I'm talking about tools a little bit. This is a library that I write or help to write. And it has lots of tuned implementations of these kinds of functions. So we're going to talk about this sort of thing later. But as always, we can always switch down to some lower level system like Pandas. Pandas has a nice frequency counting system in their series object. So you can see value counts on the series. The value counts method on the series object is about twice the speed. Okay. But notice this is sort of 2x, right? It's not 100x. We sort of expect to get 100x speed up when we switch from Python to something lower. And here we're getting 2 to 4, depending on how tuned we are. You could even compare this with Java. So here's a Java implementation. This is sort of straight, naive Java code, sort of how you would generally write it. And Java gives you, a slight speed up, not that much. Python is about 2 to 5x slower than Java when your computations are data structure bound. When you're doing lots of dynamic getting and catching and traversing data structures. Python, sort of the benchmarks I'm showing you here say that we have sort of a 2x to 5x slowdown. Okay, it's not 10 to 100. That's sort of the main takeaway from the talk. Okay, 2 to 5, not 10 to 100. OK, so given that, in lots of applications, you might actually consider staying within pure Python, not using pandas, not using NumPy. This is like heresy, I understand, in the PyData community. But pure Python is not that bad. You get lots of things. You get simple, accessible data structures. You get lists, you get sets, you get tuples, you get dictionaries. They're actually really powerful data structures. They're really powerful abstractions. They're very portable. Installation is a breeze. There's great library support around these things. You can serialize all of these data structures to JSON trivially, right? It's sort of harder to do that with a pandas data frame. You can, but it's sort of, you have to do some extra work. So by sort of staying in the core, you get lots of extra functionality. You get streaming data structures. We'll talk about laziness in a bit. I also claim you get easy parallelism, just easy embarrassing parallelism. You also get a great library for streaming analytics, which is something I'm talking about. So there's this idea, there's lots of functions that we use on lists that are useful, things like that you find in iter tools. So there's lots of functionality around these core data structures that you might want to use. OK. In particular, in functional languages, languages like Lisp or Scheme or Haskell or ML, Scala, Clojure, they often use this core data structure idea pretty strongly, and they often embrace laziness. And so there's a set of common functions that are grown up out of these languages that have been tested for decades and are sort of always in all these languages. And those functions are very useful for analytics. They're very useful for analytics, same way that pandas is very useful for analytics, but in a sort of a different class of problems. So this is my favorite function. I actually give several talks to talk about this particular function. This is the group by function. So you maybe know group by from SQL, or you know group by from pandas. This is group by just the function. So this isn't any fancy thing. This is just the function. It takes a function as an input, and that's kind of weird, right? That's an interesting piece. And it takes a collection. So here we have just a list of names. And it gives you a dictionary that groups all the items in your collection by their value under that function. So here we've got all the names of length 3, all the lengths of length 5, and all the lengths all the names of length 7. So this is sort of the core idea behind what you'd find in a pandas group by, but it's just a function, right? This is sort of the thing that's in the functional standard library that Python is sort of lacking. Python does have some functional abstractions, right? We got map, we got filter, we got reduce. Nobody likes these, right? Nobody likes these. Who actually uses map day to day? Okay, that's significantly more than I expected. We got a third of the room. Filter? And the exact same hands just went up. Yeah. Reduce? Yeah, we got like 5 of you. Yeah, and you guys are hated by your community too, right? Right. So we've replaced these with list comprehensions. We've replaced these with sort of just the basic reductions we find. But it's nice to know what these are. But there's others, like map, filter, and reduce have cousins, like really sexy cousins that you want to hang out with, right? Like group by. Group by is a really good cousin of map, filter, and reduce. You use group by every day. You just don't know it. When you write interesting code, group by is in there, just like how map is in there. So take and drop are sort of commonly found, sort of the simple things. So take and drop take a sequence and sort of a number, and they give you just a certain length of that sequence. So we're asking the first 5 of data or the last 5 of data. We can interleave some sequences together. We can do the merge part of merge sort. I've gone on job interviews, and there's like, oh, do this problem. I'm like, oh, that's really just merge sorted. And you can just pull up these functions. So there's lots of different sequence-based functions that you might find appealing. Note I'm using list everywhere, because these are all lazy. Okay, and we'll talk about laziness in a while. There's memoization, also a really common sort of functional concept that we like, missing in Python. They're actually adding LRU cache in functools 3.3 or 3.4, so that's being added. There's things like dictionary munging, right? There's a very common function for munging dictionaries. Here we got a lot of dictionaries with some data in them, and we're summing along all the values. So these sort of very common functions that you use all the time. You just always end up making your own code. Currying and pipe is a little wackier, but if you're a functional programmer, you might like currying. You might like pipe. If you're a Clojure enthusiast, you might recognize that with both of these, you can get the thread last macro. But that's the scary part of functional programming. I'm going to use pipe a bit actually later on, so I'm going to show it off. So pipe takes a bit of data, like the number 3, and then a sequence of functions, and it applies those functions in turn onto the data. So we take 3, we double it to 6, we double it to 12, we turn it into a string 12. So it's sort of a very nice way to compose lots of functions onto data. Okay. So once you sort of have this sort of grab bag of functions, you sort of do lots of analytics in an easy way. So here's word counting. We've got a function to stem words, and we're going to take our sentence. We're going to split it up. We're going to stem each word, and we're going to call frequencies on it. Okay. So once you start thinking this way, once you have this sort of set of functions, I claim that you can do most analytic problems. It's sort of just a dozen functions or so, 2 dozen. So write 2 dozen functions, you're sort of set. And again, these functions have been sort of refined over years in the functional language community. So I write this library called PyTools, and they're all in there. So PyTools, so there was itertools and functools. I claim that they're not complete, so I added new libraries with the Z instead. We also had dicttools, and that became tools. PyTools is composable. All the functions can interact with each other very easily. It's lazy. We support laziness whenever possible, so we support streaming data sets. They're also pure, so none of the functions have any side effects. Okay. PyTools, so PyTools is this library of all the functions I just showed you, plus a few dozen others. All of PyTools is low tech. Most functional programming things you'll find in Python, people get really excited about some syntax or about some wackiness. There's like a macros, MacroPy exists in Python, right? So you might this is not scary. This is the non-scary functional programming library, so I'm going to claim. They're tuned. We've actually benchmarked all of these, or most of them, and they're pretty much at the speed that Python can handle. Most of this is not my work. There's a lot of other people's work. They're also serializable. So anything produced by tools doesn't introduce any serialization issues. This is an interesting point if you want to go to parallelism. That doesn't make sense. Don't worry about it. It's also, I think, one of the most mature in terms of software practices libraries I've seen. It's very, very small. It's very, very easy to do this well. We have 100% test coverage. This is asserted by Travis CI. We have much more doc strings than we have actual code. And again, this wasn't sort of our design. We just sort of implemented a design that's been around for a long time. So that same way that NumPy inherited from some sort of APL and MATLAB, and that Pandas inherited from R, we're just sort of copying what's been out there in other languages. These are contributors. The project was originally started by myself and John Jacobson, and then lots of other folks came in and did all the hard work. We just sort of set up tests. Particularly Eric Welch has sort of taken it over. So here's word counting. Take a file name, open it up, strip each line, split each line to a set of words, take each of those lists of words and count them to one long list of words, stem each of the words, and count frequencies. So this looks natural to me, but it might not look natural to you. It's sort of weird. If you've programmed like Clojure before, this looks great, but presumably we're not at Clojure data. So you can still use these concepts inside of your standard workflow. PyTools is just a set of functions, so this might look better to you, and that's fine. Okay. So here's a slightly more complex example. Here's the yeast genome. I've got a data directory with lots of FA files. Is that FASTA? I'm not quite sure. Yeah, FASTA, the bio people, the 2 bio people here knew. Yeah. I got lots of files in there with lots of data. I think it's not so much. The yeast are pretty simple. But here's a couple of the files. And I'm going to produce one long string of base pairs out of that set of files. So I'm sort of munging some data. I take my file pattern, I get all the file names, I sort them, I open each one, I drop the header. You might have noticed that there was a header here that we didn't want. And then sort of do the same concatenation trick. And what's nice is that tools is lazy by default. So we do a little bit of work and we just pay a little bit. And we do more work, we pay slightly more. But even still, this is actually quite fast. Here's 1 million base pairs out of this weird file structure in 30 milliseconds. So honestly, for a lot of problems, this is probably fast enough. Here's a Markov chain. So given a sequence, we're going to take each successive triple of that sequence. We're going to count frequencies on each of those triples. Then we're going to sort of munge them around. So we have things like this. We want them to look like, they got wrapped around like that. We're going to merge them all together. Again, this shouldn't make sense to you right now. It makes sense to me, because I know the dozen functions I need to know this. I recommend that you learn those dozen functions too. They're a nice dozen functions to know. It takes 8 seconds, not super fast, but it's all right. James Powell gave a great talk earlier today about generators. He mentioned that you should try to have composable pieces, right? So Markov has nothing to do with the genome sequence. We can easily do a Markov chain on the words we found before. So this idea of composability is really nice. OK, I was happy with that 8-second time. That's actually pretty close to sort of how Java would do it, sort of 2 to 5 times, right? That's sort of the barrier. But so the second contributor on PyTools, and now honestly the main contributor, is this guy Eric Welch, who has been awesome. Not only has he really benchmarked a lot of PyTools, but he also re-implemented it all in Cython. So I'm about to show you SciTools, which is the same exact function set, but now implemented in Cython. We'll talk about how that's sort of interesting. If you like this, I had heard that Eric was on the job market, or about to be on the job market, I think. So I asked him to send me some business cards. I would love for him to come out to the Bay Area. So if any company here is hiring Python developers, maybe 1 or 2 out there, if you like this, you might be interested in talking to them. OK, so PyTools provides utility functions for core Python data structures. Again, we're just talking about lists, dicts, tuples, and sets. And I claim that that's enough for lots of cases. It supports streaming, composition, parallelism, and they're pretty fast. SciTools does the exact same thing on the exact same core Python data structures, but is significantly faster. It's an interesting project from a sort of general ecosystem point of view, and that is the first one I know that completely re-implements another project. So the SciTools project satisfies the PyTools test suite perfectly. We actually have tests to make sure that the doc strings are the same. So it's a perfect drop-in replacement. And so while it uses C or Cython, it's important to notice that it's actually working on your dict and on your list, on your tuple. So you don't have to sort of switch out to any other system. So here's what we had before with this yeast genome. And when we just switch out just the import statement, we get a significant speed up. And then notice this is again like sort of the 2 to 5 times you were talking about before. So this is actually pretty nice. I should also note that both PyTools and SciTools are pip installable and trivial. They work on Python 2, Python 3 with a single code base. They're easy to use. We had this frequency benchmark from before, right? We were counting sort of the frequencies of names. And SciTools comes at it right about Java speeds. Actually, depending on when I run this notebook, SciTools will beat Java or not beat Java. So really, if you're using lists and dictionaries and tuples, SciTools is competitive with a low-level language like Java. I call Java a low-level language in this context. So this is sort of interesting, right? You can actually play with Python. And if you are using dictionaries and lists and tuples, if that's like your space, you can use Python guilt-free, right? That's sort of what I've taken away from this. From a numerical ecosystem perspective, SciTools is interesting because we usually either deal with Python on Python data structures, or we use C on C data structures. SciTools sort of does this weird mix where it's C speeds, but on Python data structures. So there's no data structure impedance mismatch. Now, you wouldn't use SciTools to, say, do a matrix multiply. That would be dumb. But you would use it to build a Markov chain. OK. So we can take, so I showed you the yeast genome and the code to compute on the yeast genome. We can do the exact same thing with the human genome, which I think on my disk is like 10-ish gigabytes or something. Maybe there's a lot of files in there. I'm not sure what's what. I honestly have no idea what I'm doing. But I have a directory that has about 15 gigabytes of text files. And this is doing my genome stuff on that 15 gigabytes. And it runs in about 10 minutes. Okay. So again, not super fast, but it is 15 gigabytes. My laptop has 4 gigabytes of RAM. I didn't have to think about streaming algorithms. It would all just sort of naturally fill out. And so here, actually, so the data is interesting. There are some files in there that have some junk in them. There's this n base pair that shows up. And so if you had known about your problem, you could have done this computation much more easily, sort of a 4x4 array, 4x4x4 array, and just sort of put in numbers. But you wouldn't have been flexible enough to handle this weird case that there's some n. So there's some missing data happening, some weird data happening. OK. One of the nice things about parallelism, I think, is sort of really driving the recent push behind functional programming, is these notions of parallelism and concurrency. And functional programming has a history of handling that well. So, right here. Right, so I'm going to slightly change my computation. I used to produce one long sequence out of all of my files. Now I'm going to compute one sequence out of each file and compute my Markov chain on that and merge them all back together at the end. So, oh, there's supposed to be an F right there. So this is I'm talking about parallel map, PMAP, for a bit. And so PMAP is just like map to start out with. I'm going to take my file pattern. I'm going to compute a Markov chain on each file. And then I'm going to merge them together in this nice way. So I'm distributing my computation on the file names. I get back some Markov chains, and then I reduce them with this. Okay. And now note, I mean, this is just a sequential computation because I've just renamed PMAP to map. So this is how I test my code. And then I switch out to using multiprocessing. Okay. And I use the exact same command. So so this PMAP abstraction is a really nice thing to have. In order to use this well, you need serialization. Tools helps you with that. Go to the tools docs if you care. And you can also switch out to, oh, there we go. Now we have the full thing in there. Switch to IPython parallel. Most parallel runtimes, I'll say, have some notion of PMAP. So if you know those, you can just write your standard code and just sort of annotate the section that you care about with a PMAP. And then you can sort of use whatever backend you like. So I got this to run with the multiprocessing system. I got this to run on I think I was using 8 cores on a 16-core machine. I got it to run like 2 minutes. So that was my speed up from like 10 to 2 with 8 cores. So not bad. Okay, so PyTools is not unique. Python is by design an imperative language. Like if you ask Guido about this topic, he will say negative things, not negative things, but he'll say positive things about imperative programming, about its readability and about its simplicity. So by design, Python is not a functional language, but it has all the ingredients to include lots of nice functional concepts. This is not unique. So the sort of standard library, in order to you find it in lots of languages. I personally like Clojure. PyTools is modeled after Clojure, but you'll find the exact same set of functions elsewhere. But to make these functions, you only really need 2 sort of language features. You need functions as first-class objects, and you sort of need lazy iterators. But that's all you really need. If your language has those things, then you can implement all of these functions and sort of all the rest of the things that are in tools. There's lots of things in tools. So any language that has these attributes, you're sort of set. So in Python, there's lots of projects that do this. fn.py, I think, has the most stars on GitHub, so you want to check that out. Funky, it also exists, and it's sort of fun. They've got a different set of functions, but they're a neat set of functions. There's more iter-tools, and there's tools. In JavaScript, there's underscore.js. This is probably the most popular example of this sort of project. So when I actually work in JavaScript, I just import underscore, and I pretty much write tools code, and it all works out. So there's this really nice sort of cross-language set of functions that you can use. In C#, in the .NET platform, there's LINQ, which takes more from relational algebra, from SQL, than it does from functional analysis, from functional programming. But that's also sort of a good case of injecting functional languages into imperative by design languages. I would love to see this happen in Julia. If anyone's active in that, it's a good project to do. It's very easy. The spec is already out there. And I'm also actually sort of interested. So Java 8, I'm not sure anyone knows, but Java 8 has functions as first-class objects. And they've always had lazy iterators. So you can imagine Java becoming much more pleasant to write in from a functional perspective. So I'd love to see that happen too. Right, so I give a talk at PyData New York, a tutorial on sort of why you should like functional programming from a design perspective. I've tried not to hit the design too much. I'm talking about performance here. But you should go check that out if this sort of thing interests you. Very quickly, functional programming will just make you a better programmer, generally, even if you don't use it in practice. composition in large projects ends up sort of increasing accessibility and scalability. Pure composable functions are very easy to test by nature. Sequence abstractions give you this sort of streaming ability. Like I was able to compute this genome, this large genome on my small laptop. I needed, I think, like 2 kilobytes of data, 2 kilobytes of RAM. So all that was sort of necessary in order to perform that computation. And that sort of falls out when you use these ideas. And then there's this idea of purity and serialization for parallel distributed computing. So good ideas fall out of this paradigm. Just look into it. Right, so PyTools has an interesting history. So I like the language Clojure. I think you guys should also like the language Clojure, but probably you won't. No one. Yeah. So so I need to interact with C and Fortran code. So my sort of day job, I interact with numerical linear algebra. That's sort of what I do normally. And Clojure, that's not a language which to do that. So Clojure is a Lisp on the JVM. You might be interested to know. And for most people in this room, both of those words are probably ugly. Certainly in my community, Lisp and JVM are both like verboten. So I couldn't code in Clojure. But I found that I didn't really need a whole lot of the things that were in Clojure. I really just liked the sequence abstraction and the standard library. I didn't really need macros. Not all the time. Most of the functional programming I do, that sort of day-to-day stuff, has nothing to do with macros or monads or algebraic type systems. It's just sort of this nice set of functions that I like. So I originally made itertools and funktools and dicttools to sort of model off the standard library versions with S on the name. And I sort of imported those all into tools. And then a bunch of other people came by and made them all faster. I routinely get a pull request like, hey, your merge sorted routine could be using the heap queue algorithm in the standard library. Here you go, it makes it 40% faster. That's sort of like the standard pull request for the last few months in PyTools. And that's, it's rare to find a function that's not faster in PyTools that you could write yourself. This is so these are people who have helped out. Again, I said, this is a joint project between John and myself to start out with. And then lots of people came on, and then Eric Welch hopped on and sort of has taken it. SciTools, as large as Eric Welch, and a few new contributors with a lot of inspiration coming from Clojure and from Underscore. That's it. So main takeaway, for data structure bound computations, Python is 2 to 5 times slower, not 10 to 100, if you trust my benchmarks, which you shouldn't. Functional programming, not a bad idea. You don't have to be scared by it. There's things in functional programming that you can like that don't require you to understand type theory. There's just a few good ideas that are really the important ones you should think about. Tools is a nice library. Just typing pip install tools at some point might make your life better. And then if you were to use tools, try out SciTools, and everything just works. It's really nice. And that's it. Thank you guys for your attention.
So that piping example, or the pipe function, looks really awesome.
Mm-hmm.
I was
Everyone
wondering, so I was wondering, are you able to extract an element from the end of the pipe before you finish processing the input? So, for example, if I gave you like an infinite generator, could I just start popping things?
Yeah, you would just say take 1, take 2. Or,
okay.
Yeah, I mean, so all pipe does, you take data, you apply a series of functions onto it. If those functions are lazy, then you're good.
Okay, but
I think
your
I've always
examples
ended
used like normal map instead of like IMAP.
Mm-hmm.
So would you have to pass in the correct lazy?
Yeah, so there's a map in tools, and it's IMAP. It's IMAP in Python 2, and it's Python 3 map in Python 3. So all tools functions are lazy if they can be. So I'm actually, when I did from tools import star, I actually pulled in, the IMAP if you're in Python 2. Yeah. So tools handles the most things. It's also what I use for Py2.3 compatibility a lot of times. If I need a map that's lazy in both Python 2 and Python 3, I just import it from tools. Does that answer your question?
Yeah. Thanks.
Thank you for the talk. It's really interesting. I like to see these concepts. My question is, what's the relationship between the iter tools and func tools and the standard library? If they are, it seems like you're doing it pretty much the same thing but faster. And if that's the case, why not put those in the standard library?
Right. Yeah. So I'm not doing the same thing as itertools and functools. They're also fast. Like they're implemented in C. They're great libraries. If I ever want to do combinatorics or some sort of permutations thing, I go to itertools with an S. Great library. I would claim that there's some things that are missing. That's sort of my approach. If you're used to functional programming and you come to them, you're just like, wait, this thing isn't there, that thing isn't there. Some things don't match up. And so I think of itertools and functools as being complements to the standard library. The second question was, why not contribute this back to the standard library? I honestly don't feel a whole lot of need. I think that the like GitHub and pip pretty much handle the distribution system for me, I think. I suspect that any contribution I would do wouldn't go into 2.7, which would be an issue for me. There just isn't much of a need. Like, I think that the distribution around Python packaging is sufficient to distribute this without it being packaged in the core system. But it's a valid point. People brought it up before. Yeah.
You're showing the Markov chain over there. It was quick all the time when you showed it. Is it part of your library, or is it something that you do, or can you explain it in a few words? Because where's the matrix here? This is what I'm missing.
So no, this function is not part of tools. It's just part of this presentation. What I claim is that you can make relatively complex operations with a small set of functions, and those small set of functions have been refined over decades in the functional paradigm. You asked about a matrix, and this probably doesn't classify as a Markov chain exactly, but I'm associating to a pre-sequence a mapping of the next element and a count. So I'm going to retract my Markov chain claim, and I'm just going to say that I'm counting. Let me go back to. We're almost there. Right. So given a sequence, I make a thing like this. That's what I'm going to claim. So I'm not quite sure what you mean by matrix in this case. But so the results here is that if I've seen an A and then a T, what's the next thing I'm about to see? And historically, what I've seen is this. I've seen 300,000 A's, 200,000 C's, 200,000 G's, and 350,000 T's. So maybe my next thing might be a T or an A. It might not be a. Yeah. So that's the computation. Yeah. Sorry. So you can divide this a little bit and get your answer. There's a guy over there.
So you said in one of these tests you had 15 gigs of data with a few kilobyte memory footprint.
I said I could do it in a few kilobyte memory footprint.
Okay. How far do you think you could push this? I mean, a terabyte of data? I'm thinking, is this a reasonable set of tools to think about for sort of the medium data space where you're still you have more data than would fit in RAM, but it's still not, petabytes
right.
or.
Yeah. So. So what really the thing that I'm leveraging here is streaming algorithms, right? The idea that you actually don't need to hold on to all of your memory at once. You can sort of walk through it. And I think that streaming is definitely a good candidate to handle medium data sets. I was able to compute 15 gigabytes in pure Python with scitools in 10 minutes. If you had a terabyte, you wouldn't mind waiting a few minutes, a few hours, you'd be fine. So definitely streaming is a good candidate for medium-sized data. You're just sort of bound by computation. You're not bound by memory. Does that answer your question?
Yeah, thanks.
Great.
One comment I would have on this is that you've implemented functional tools in imperative language, but you haven't shown us a comparison of functional tools built in a functional language. I would expect that there would be a huge speed difference between what you're doing here and what you would see in like ML or OCaml or skiing with chicken or something like that. And so just a comment, if you want to take this concept farther, actually evaluate what tools the functional community actually use to speed up their code.
Are you expecting functional languages to be faster or slower?
For these operations, I expect them to be faster.
Okay. That has not been my experience. I haven't tested with the ML family languages. I have tested with the Lisp family languages, particularly Clojure, a lot.
And that's a JVM. So,
okay.
But if you take like the chickens compiler, which it actually is a compiler, on top of these concepts. So
That'd be fun. So no, I haven't done that. Sounds like a good opportunity. I don't think that I would. I guess I sort of have some implicit trust in Java to have implemented these sorts of things well enough. You're laughing now, but I mean Java's pretty robust, right? There've been a lot of eyes working on Java. But no, I can imagine a Haskell implementation or a OCaml implementation being faster. I would not expect it to be 10 times faster. Is that it? Looks like we're done. Oh, one more.
Just a general question. A lot of the benchmarks that you looked at are doing a lot of string processing, and for some reason, maybe this is bad intuition. I kind of expect Python to do a little bit better relatively if you're doing string munging, and I'm just curious what you think the high level versus low level speed difference would be if you were working on a numerical set of bytes in Python versus something that was kind of hand coded in C, moving through these bytes.
Your question's making me sick. Yeah, so, oh, wow. Okay. Yeah, it just, no, so in numerics, something like pandas is quite a bit better, actually, if you give it numerics. So I've chosen strings here for a reason. Again, oh, man. Right, so a good example is if you look at this operation, and you can see, you don't have to do this operation the way I've done it with these data structures. You could write a 4x4x4 array of integers. Whenever you see an A, you put into the 0, you see AAA, you put into the 000 slot. AAT, put in 00, 1 slot. You could do this much better if you knew numerics ahead of time. Particularly also if you knew you only had 4 letters coming in. So yeah, so when you switch down to numerics, you get some more, you get more to crunch on, right? Lower level languages can do a lot better job. So
what do you think about a streaming version that runs on NumPy arrays or a wrapper on HDF5? Would that be faster still? The same functional ideas?
Oh, well, hold on. I mean, for this sort of operation, if I don't know my words ahead of time, if I don't know my data is going to come in ahead of time, then it's hard to map down to a NumPy-like system, right? I'm really talking about the case where you're in this dynamic mode, where you get sort of weird data coming in, you're using Dixon lists because you have to. If you don't have to do this, please use numerics. Like, numerics are faster. Then you get this sort of then you're sort of in the 10 to 100x speed up regime. But if you have this sort of like weird heterogeneous data coming in, you need to handle it dynamically. My claim is that Python has sort of this 2 to 5x regime. If you did this same experiment with just pure numbers, I think in pandas value counts, for example, they actually have a separate switch to like do something else. I think numpy.bin counts if your elements for frequencies, if your elements are purely unsigned integers between 0 and like whatever, it can do this operation very, very quickly. Right? Then you're in like a different algorithm. But yeah, so general idea, like don't do this if you don't have to. Only do this when you actually have to. And you can, if you understand enough about your problem, you can almost always switch down to the numeric system. Right? This is sort of what you do first before you optimize. Any other questions? We're also out of time. We have one more? Yeah.
Before this example, you had another one, a long sequence in the pipe. You went for it quite fast. Can you just go slowly and explain someone who takes a bit more time to understand actually what's going on here and each time? And I understand why it's better, but if you can pinpoint where it's much better, then it will help.
Well, first of all, I don't claim this is better. This is just different. I think a lot of people would say that this is much worse. To my aesthetic eye, it's maybe better, but I would never use this in production code because people I work with wouldn't appreciate it. Okay, so pipe takes a piece of data and then a sequence of functions. And it takes that data and applies those functions in turn onto it. If you're with Clojure or some Lisp languages, there's just the thread last or thread first macro. I use map here to denote that I want to do that operation onto everything in the sequence. Okay, so I take some file pattern, like something you might type into ls to find a list of files. I sort that list of files. I then open each file. Okay, and notice that this is happening lazily, so these don't actually open all at the same time. I then drop the first line of each of those files. So drop and take were these sort of islice things.
Can you say the lazily again? What does it mean? It's like it doesn't go, it goes each file one by one, or does it treat them all in parallel? What happens there?
So a file is like a sequence, and so it's going to open up one file, it's going to pull off each line, and it's going to do all these things to it, and then it's going to open up another file and do all the rest of the things. But it will only do that as I ask for information. So if you want, generally speaking, good answer is go to the tools.readthedocs.org, and there's lots of documentation there about all these ideas. But let's talk afterwards. I think there's a longer conversation. We're out of time. So thank you guys.